Hi everyone, so today I want to talk about crystallographic directions and how to kind of define them and draw them within a kind of conventional cubic unit cell, which is something you kind of see quite often in material science. So one of the first things that we want to start off with when describing or talking about crystallographic directions is we kind of use a different kind of or unique coordinate system, similar to kind of what you've seen previously. So as usual, you're used to your X, Y, and Z, or if you've done mechanics a lot, you might see the number notation. But here we're going to introduce these Miller indices. Miller indices. And so Miller indices, we use H, K, and L for the coordinate systems here. So, and when we use, basically for crystallographic directions, we're going to use these square brackets here. So square brackets denote directions. We'll see there's different notations for planes and families of planes and families of directions as well. So with that in mind, let's erase here real quick, and we'll draw our kind of nice cubic unit cell and start to define directions. So let me draw this one more time. HKL, and let's draw our unit cell. Perfect. So for a crystallographic direction is essentially the same thing as a vector. So how we're going to define our vector is we're going to look at the coordinates of the finish and the coordinates of our start, and we're going to go finish minus start, and then that's going to give us our, when we subtract those coordinate systems, that's going to give us our direction. So let's start off with someone that might be a little bit straightforward. Let's draw the 100 direction. Well, I'm just going to start at our origin here because it's nice and convenient, because our start here will just be 0, 0, 0. So if I want to do finish minus start, I know that this point is 1, 0, 0. So my finish minus start, 1, 0, 0 minus 0, 0, 0 gives me our direction that we wanted. So that was your first crystallographic direction. So let's do a couple more. So let's draw 1, 1, 0. This one we could still do the same thing here and start from our origin. Nice and simple, straightforward. And the 1, 1, 0 would just be like this. Excellent. So what about if I have a negative direction, or a negative, essentially, number here? Well, let's draw that one. Let's do 1, 1, 0. You see how basically I used here for our negative notation? So negative, put that hat on it. So the hat over in the number, that means it's equivalent to -1 here. Or same thing, -2. Erase this. So here's a little bit trickier. We need to kind of be a little bit strategic in choosing our direction, or our start and our finish vector. So for this one, I'm going to start here, and I'm going to end over here. So my finish is 1, 0, 0 minus my start, which is 0, 1, 0, and that will give me 1, 1, hat, 0. So not too bad. You just kind of have to mix and match and play around with what coordinate in my unit cell is going to give me the direction that I'm looking for. And alternatively, if I were to draw a direction, so let me draw actually a tricky one here. Let me draw this. Let's see if you can get this. So same principle like usual. So finish minus start. Now my finish here is actually half, 1, and my start is 0, 0, 0. So you might be tempted to write your direction half, 1, but typically with Miller indice notation and when we're defining crystallographic directions, we want to kind of multiply out and get integer values So this will actually be 1, 1, 2 direction, just multiplying by 2. That's it. So you can repeat this procedure. So you can, draw your own vectors. You can analyze what vectors or what directions you're looking at in your crystal. Now, one cool thing I kind of want to note is that there are certain directions, especially in cubic crystals, that are crystallographically equivalent. And what I mean by that is that you can imagine, let me kind of erase and redraw my crystal. So let me redraw my unit cell, just like we did previously. Now let's look at a couple of different directions. So let's look at our old friend, the 100 direction again. Now you can imagine if I were to kind of blindfold you and then I could rotate this crystal, and specifically if I rotate it kind of along or around this k-axis, essentially, you could not tell essentially the difference between the 110 direction and the 001 direction, right? So if I blindfolded you and I rotated that crystal, you wouldn't know the difference between this direction and this direction. Similarly, you could do different rotations and you could see that you couldn't tell the distinction between that direction and this direction. And you could do the same thing for the kind of negative values as well. Sorry for getting a little messy here. Let me do that. 0, 1, 0. So what we call these directions that are basically have the same magnitude, so that's one critical condition for crystallographically equivalent directions. It's the same magnitude. And they will pass through the same atoms, essentially. So you can imagine in a simple cubic cell where we have all the corners, you see they pass through the same number of atoms, and here the atoms would essentially overlap the entire direction. So they basically see same atoms. Basically, they pass through the same number of atoms. So what we would call this is a family of crystallographic directions. So they are crystallographically equivalent, and so we would write all these 6 directions as 100 directions. In cubic materials, there's also 10 directions and even 11 directions. So those are basically the essentials of how do we define or kind of draw crystallographic directions. Basically, you just use, remember, your start, finish minus start position in your vector, and then crystallographically equivalent directions are ones that have the same magnitude, they see the same number of atoms, and they basically pass through the same number of atoms and the same distance between them. So yeah, that's all we have so far on crystallographic directions, and the next video we'll move on to how to draw crystallographic planes. Thanks.